Hi, in this video we are going to implement the Fibonacci sequence problem together, and I have already created a app.java and a Fibonacci algorithm.java. We are going to write the source code here. So first of all, I'm going to implement the naive approach, and it's going to have a public integer naive Fibonacci. It's going to get an n as a parameter. And we have discussed that if the n is equal to 0, then we have to return 0. And if the n is equal to 1, this is the so-called boundary conditions or whatsoever, return 1. So it means that the first item in the sequence is 0, the second is 1, and then we can use our recursive formula for calculating the other items with the help of this, as we have discussed in the previous section. So the third item will be 1 again, because we have to use the n-1, which is 1 plus 0, which is equal to 1. Okay. And anyways, if n is greater than, it is not 0 and it's not 1, then we have to return, and we have to use a recursive formula, naive Fibonacci, n-1 plus the naive Fibonacci n-2. Okay. So let's see how it works. Of course it is going to work. So I'm going to instantiate the Fibonacci algorithm. It's going to be equal to a new Fibonacci algorithm. And of course I'm going to print out the Fibonacci algorithm dot naive Fibonacci. For example, the 0 should return 0. So the 0 item is 0, the first item is 1, the second item is 1 again. So if n equal to 3, then it is going to return 2. If it's 4, it is going to return 3, then 5, it is going to return 5, I guess. Yeah, so it's working fine. And what's the problem? Because we use recursion without memoization and dynamic programming, there's lots of overlapping subproblems, and we keep calculating the same problems over and over again. So this is why it is working fine. But we should use memoization. So let's see. I'm going to create a map and store integers. Integer as an index and integer as the value. This is going to be the memoized table. Not a good name, but anyways, it's going to be a hash map. Okay, maybe it would be a better solution to instantiate it here. Okay, so this is the name. Sorry, I get rid of this. Okay, I'm going to import the map and the hash map. Okay, it's working fine. I have to set the boundary conditions, as we have discussed, that whenever the index is 0, the value is going to be 0. So it is equivalent to this statement. When the index is 0, then the value will be 0. Whenever the index is 1, then the value will be 1. Okay. And because we use this memoized table, we can get rid of this statement. I'm going to create a public integer Fibonacci memoize. Of course, we have to specify the n again. And it's very important that we can use, because we use a memoized table, a hash map, and it's very important that the time complexity for putting and getting element from a hash map is constant time complexity, very fast. So we can check whether that memoized table that contains, if it contains the key n, then we are not going to compute it. We can return this, that memoized table that get n. So it's very good because we don't have to calculate over and over again the overlapping subproblems. If the memoized table contains the item we are looking for, we just look up the memoized table. We can do it in constant time complexity very fast, and we just return it. Okay. And else we know that our memoized table does not contain our item, so we have to calculate it. So memoized table.put. First of all, we have to calculate the n-1 item, and we have to call the Fibonacci memoize recursively for the n-1. And it is going to put with the index and the values accordingly. It is going to work fine. And of course, that's what we are after. Of course, we have to calculate the n-2 index. So I have to call the Fibonacci memoize again, but not for n-1, but for n-2. And why is it good? Because we can get the calculated number. We don't want to recalculate it because we have already done it. It is in the memoized table. So I just have to get from the memoized table n-1 plus this, that memoized table that get n-2. Why is it good? Because I have already calculated it. We check whether this is in the memoized table. If it is, then no problem, we just return it. If it's not, we have to calculate it in a recursive manner. We can't do any better. We have to calculate it once. We calculate it once here. We call this method recursively and insert it in the right index, in the right position. And whenever I want to calculate the number, I just get it because I have already inserted. So I just get it from the memoized table. Of course, I have to put it in the memoized table because this calculated number is not in the table. We get the two items and add it together. And of course, I have to put it for the index n and the calculated number. So if we see that if this n is in the memoized table, we just return it. If it's not, we calculate it with half of recursion, as we have seen like this, and we keep inserting it for further consideration. We know that in the future, maybe we will use this number, so we will need it. And I'm just going to return the calculated number. Okay. And I don't have to specify these conditions because in the memoized table I have already done it. So let's see. Fibonacci memoize, for example, 5. It is going to work fine. The 0 item should be 0. Okay. The 1. If n is 1, then 1. Yeah. If n is 2, it should be 1 again. If it's 3, it should be 2. And so on. So it is working fine. So I don't want to repeat myself, but the very important part, and this is the principle of dynamic programming, that here we calculate overlapping subproblems over and over again. Here we use a hash map. We could use, for example, array list whatsoever, because in Java a hash map is implemented very, very efficiently. We can use it very fast, constant time complexity. And we can create such a memoized table and make sure that if it has been calculated, we don't want to calculate it again. We just want to return it. And anyways, we just calculate it and put it in the memoized table for further consideration. So that's all about memoization for Fibonacci numbers. Thanks for watching.